In lesson 5, we have seen that the association between a linear map and a matrix is a natural operation. In fact, it involves only linear combinations, which are the most natural operations that we can perform in linear algebra. Due to this remark, we expect that if we define operations on linear maps, then we can easily translate these operations onto the associated matrices. We're going to see that this is indeed the case. Now, since linear maps are functions, if we want to define operations on them, we need to work in a functional space. Recall that this is one of the three examples of vector spaces that we have examined immediately after the definition of vector space, and it consists in the set of all functions defined on a set X into a vector space E endowed with a pointwise linear structure. Remarkably, we have seen that this is an infinite-dimensional vector space. In this chapter, we are not interested in generic functions, but in linear maps, which need a vector space for both their domain and range, and they have the property of passing through linear combinations, which is of course something that is not verified by all the functions. And so, the set of linear maps constitute a particular subset of a functional space. Moreover, thanks to their linear behavior, it's easy to see that the set of linear maps between two vector spaces V and W is not only a subset of F of V and W, but it is indeed a vector subspace of this functional space. And to underline the importance of the linearity of these maps, we substitute F with the symbol L. We are now going to formalize this introduction with the definition of the vector space of linear maps. Given two vector spaces V and W over the same field F, this is important, we indicate with the symbol L of V and W the vector space of all linear maps F between V and W endowed with a pointwise linear structure. That is, if F and G belong to this space and lambda belongs to the set of scalars F, then the sum of two linear maps acts punctually on a generic element X of V in this way. So we sum F applied to X and G applied to X, which belong to W, and so they are vectors, and we know how to sum them. In the same way, the linear map lambda times F is simply lambda times F of X for all X belonging to V. The request of linearity for the functions belonging to L of V and W reduces enormously the dimension of the functional space of all the possible functions between V and W. In fact, the dimension of this vector space is finite, and in particular is the product of the dimension of V and the dimension of W. So the take-home message of this page is the following. Whenever you have two vector spaces over the same field, you can construct a third vector space, that is, the vector space of all the linear maps between the two vector spaces. We are now going to see that the operations of sum and multiplication by a scalar can be translated into analogous operations on the matrices associated to the linear maps. To be precise, the data are the following. F and G are two linear maps between vector spaces V and W of dimension n and m respectively. BV is a basis of V with vectors Vj, and BW is a basis of W with vectors We. And finally, A and B are the matrices associated to F and G respectively with respect to the bases BV and BW. We indicate the matrices AB with their entries Aij and Bij. Now, if you go back to the definition of matrix associated to a linear map, you see that these entries here of the matrix A are exactly the coefficients that appear in the expansion of f of Vj on the basis Bw. Similarly, the entries Vj of the matrix B are exactly the coefficients that appear in the expansion of G of Vj over the basis Bw. So if you apply the function sum f plus g over the jth vector of the basis Vj, thanks to the pointwise linear structure, you can decompose this into the sum of f of Vj and g of Vj. We have just recalled that in terms of the entries of the matrix A and B, this can be written like this, and using the property of the sum, we can write it in a compact way like this. So you see that if you forget what is written in the middle, you end up with this formula here, which tells us that the function sum applied to the jth vector of the basis BV can be decomposed on the basis BW with the coefficients given by the sum of the entries of the matrix A and B. So if we define the sum of the matrices A and B as the sum of their entries with same position, that is the same row I and the same column J, then A plus B is exactly the matrix associated to the function sum f plus g. So you see that the natural association between a linear map and a matrix paid off. In fact, there's no simpler way to define the sum of two matrices than this one here. And we have just proven that this matrix sum happens to be in perfect agreement with the pointwise sum of linear maps. To fix the ideas, let me give you a practical example of matrix sum with these two matrices here. What we must do is to operate the algebraic sum of the entries of A and B having the same position. Let's start with this one and this one. We have 5 plus minus 4, which gives 1. Let's consider, for example, this one here and this one here. We have minus 1 plus minus 1, which is minus 2, and we have minus 2 here. Let me give you a last example. You have here 0, and you have to sum it with 1, which has the same position in the matrix B, and you have 0 plus 1, 1. By definition of matrix sum, we have clearly that the 0 element for the matrix sum is the null matrix, that is the matrix with all 0 entries. Moreover, the opposite matrix, that is the matrix that sum to another matrix gives rise to the null matrix, is simply minus the matrix A. This is actually a particular instance of the matrix lambda times A, built by multiplying all the entries of A by the scalar lambda. This is the matrix associated with the linear map lambda times f, as you can check by repeating the same procedure detailed above for the sum. Let me discuss the multiplication of a particular matrix by a particular scalar, for example, A times minus 3. By definition, what you have to do is to multiply all the entries of A by minus 3. So, for example, 5 times minus 3 is minus 15. 0 times minus 3 remains 0. 1 times minus 3 is minus 3, and so on. So to recap, matrices form a set, and we have defined on the set of matrices two operations, the sum and the multiplication by a scalar, which are exactly the operations that we need in order to define a vector space. So now we can ask ourselves if the set of matrices together with these two operations is a vector space. We're going to see that this is true. Let's first fix the notation. The set of matrices with m rows, n columns, and entries in the field F is denoted like this. We say that the matrices belonging to this set are real if F is the set of real numbers, and we say that the matrices are complex if F is the set of complex numbers. In particular, if n equals m equals 1, then the matrix is just a scalar of F. The fact that the set of matrices, together with the operation of sum and multiplication by a scalar, is a vector space is guaranteed by this theorem here, which says that the dimension of this vector space is n times m. So, if we consider two vector spaces V and W over the field F with dimensions n and m respectively, we have that the dimension of L of V and W is exactly n times n. For this reason, we have that the space of matrices is isomorphic to the space of linear maps. In particular, we have that the vector space of endomorphisms of V, that is denoted like this, is isomorphic to the vector space of square matrices that is denoted like this, because they both have dimension n square. Let me recap. Consider two vector spaces V and W of dimension n and m respectively, a linear map F between them, fix a basis BV and a basis BW, and then associate to F the matrix A. This function belongs to L of VW, and this matrix belongs to m times n of F, where F is the field over which V and W are defined. We know that the association between F and A is a bijection, and it is also linear. And so we have that there is an isomorphism between the vector space L of V and W and the vector space of matrices of dimension m times n. It is important to remark that the isomorphism also involves the linear structure. So if we have two functions f and g belonging to L of V and W and a scalar lambda belonging to f, then we have this correspondence. Lambda times f corresponds uniquely to lambda times A. And if G is associated to the matrix B, then we have that F plus G is associated to A plus B. So, to conclude, we have not only a perfect correspondence between a linear map and its associated matrix, but also between the operations that we can perform on linear maps and the analogous operations that we can perform on the associated matrices. Because of this duality, it is not surprising that we can define also a canonical basis for the vector space of matrices. This canonical basis is given by all the matrices indicated with Eij, which have all null entries except for the ones in the position ij, where their value is exactly 1. Consider the vector space of real matrices of dimension 5 times 4, so with 5 rows and 4 columns, like this, you see? The matrix E23 belonging to the canonical basis of this space is the matrix with all null entries except for the second row and the third column. So we draw the second row and the third column, and their intersection is exactly this entry here, whose value is 1. Let me show you why this has all the right to be considered the canonical basis. Consider a vector V belonging to Rn. you can write V as x1 xn, and so xi with I that goes from 1 to n, and you know that you can write V like this. V is the sum for one that goes from 1 to n of xi times ai, where ai is the ith element of the canonical basis. Why that? Well, if you write x1 times a1, which is 1, 0, etc., 0, plus xn times 0, etc., 0, 1, and you operate the sum, you have x1, x2, etc., xn, which is exactly V. Since matrices have two indices, we cannot expect to have exactly this decomposition here, but we must expect this decomposition here, and this is exactly what we're going to find. Let's prove it in the case of matrices 2 by 2. Here you have the generic expression of a 2 by 2 matrix. The matrices of the canonical basis of M22 are these ones here, and as a small exercise you can verify that the computations that I perform here are exact, and you recover the matrix A. Okay, we have concluded this section. In the next one, we examine the possibility of associating a matrix operation to the only operation on linear maps that we haven't considered yet, that is, their composition. In this section, we show that it's possible to associate to the functional composition of two linear maps an algebraic operation on the associated matrices that is called matrix product. Beside the natural mathematical curiosity to explore a new operation, there is also a practical motivation to study matrix product. In fact, this is the most important operation involved in the functioning of neural networks, which are the building blocks of artificial intelligence systems. The elements that we need are displayed in this diagram here. We have three vector spaces over the same field, U of dimension r, V of dimension n, and W of dimension m. BU, BV, and BW are of course fixed bases for these vector spaces, and F and G are two linear maps, F from V to W and G from U to V. Hence, the composite linear map F composed with G is a linear map from U to W. Finally, A, B, and C are the matrices associated to the linear maps F, G, and F composed with G, respectively, where the bases associated to these matrices are those indicated above the vector spaces in this diagram. We want to see if there is the possibility to express the entries of the matrix C with respect to the entries of the matrix A and B. In order to do that, we have to write down the definition of the entries of the matrices A, B, and C, paying a lot of attention to the use of the indices, which is the only difficult issue in the analysis that will follow. By definition, the entries A, I, K are the coefficients that appear in the expansion of f of Vk with respect to the basis Bw. The entries Bkj are the coefficients of the expansion of G of Uj with respect to the basis Bv. Finally, the entries Cij are the coefficients of the expansion of f composed with G applied to uj on the basis bw. I'm going to need all these expressions, and so I reported them on the next page. Let's write explicitly what it means that f composed with g is applied to uj. It means that f is applied to g of uj, but g of uj has this expression here, and so we can write f applied to this expression. Now we remember that f is a linear map, and so it passes through linear combinations. That is, we can take f and apply it directly over the vectors vk. This is exactly what is written here. But now, instead of f of vk, we can use the explicit expression that we have found before. So, at the end, we have that f composed with g applied to the vector uk has this expression here. Now we use a nice property of finite sum, that is, they can be rearranged. We can exchange these two symbols of sum here. And so we can first perform the sum over the index I, and then perform the sum over the index k. So at the end, we have that this expression here can be written like this. If you take a look at the expression of f composed with g applied to uj that we have found before, we have put in light the fact that there is a sum over I of coefficients Cij times the vectors Wi of the basis Bw. So here we have exactly the same thing with the explicit expression of these coefficients Cij. This computation is the reason underlying the definition of matrix product. Given two matrices A and B, the first with dimension m times n and the second with dimension n times r, we have that the matrix product C is a matrix with dimension m times r, whose coefficients are given by the formula that we have found before. Take a good look at the dimensions. The first matrix has this dimension, the second matrix has this dimension, and the product matrix has this dimension. You can see that there is a dimension that repeats itself. This is called the inner dimension of the two matrices when they are multiplied together, and it must be exactly the same, otherwise the matrix product cannot be defined. The reason why the inner dimensions must be the same follows from how the matrix product has been defined. In fact, we have manufactured the matrix product in order to represent functional composition between linear maps. But, as I recalled here, this is defined only if the range of the first map coincides with the domain of the second one. In terms of matrices, this translates in the fact that the inner dimensions must agree. We can resume these considerations in the following theorem. Let two matrices A and B with entries in the same field F and with inner dimensions that coincide be the matrices associated to the linear maps F from V to W and G from U to V respectively, of course with respect to certain fixed spaces. Then their product, C equals A times B, is the matrix associated to the composite linear map with respect to the same basis chosen for U and W.
In the first chapter, we have introduced the concept of functional space. If X is a set and E is a vector space, then the elements of this functional space are the functions defined on X with values in E. In this chapter, we fix our attention to a special kind of vector space, namely the one given by all the linear maps between two vector spaces V and W. Remember that this functional space has an infinite dimension. However, thanks to the fact that here we don't consider all the possible functions between V and W, but just the linear ones, we have that this functional space has a finite dimension, precisely the multiplication of the dimension of V and that of W. Thanks to the fact that we can uniquely associate matrices to linear maps, we have that also the set of all matrices with m rows and n columns with coefficients in the field F is a vector space whose dimension is m times n. In particular, if A and B are the matrices associated to the linear maps F and G, then we have that F plus G is associated to A plus B, and lambda times F is associated to lambda times A. Remarkably, thanks to the definition of matrix product, we can also make sense of the matrix associated to the composition of F and G, which is the matrix product of A and B, whose entries are written here. Notice that in the same way as we can compose two functions when the image of the first agrees with the domain of the second, we can multiply two matrices if and only if the so-called internal dimensions agree.
The matrix product is often called rows times columns product for a simple reason that we're going to explain now. The generic element Cij of the product matrix can be obtained in the following way. Consider the ith row of the matrix A and the jth column of the matrix B, and combine them together as follows. Multiply the first entry of the row with the first entry of the column, like this, then write a sum. Do the same for the second element of the row and the second element of the column, then write again the sum, and continue like this until you reach the last entry of the row and the last entry of the column that you can see multiplied together here. The final result that you obtain is exactly Cij. You understand that the coherence of this computation is guaranteed by the fact that the rows of A and the columns of B have both n elements, which is a consequence of the fact that the inner dimensions of these two matrices agree. Let's immediately see an example of how to apply this rows times columns product. If we want to multiply matrix A with matrix B in this example, we first have to check that the inner dimensions agree. So we see that matrix A has 3 rows and 4 columns. Instead, matrix B has 4 rows and 2 columns. So the inner dimensions agree, and we are left with a matrix product that has dimension 3 times 2. It will take too much time to detail all the computations for the entries of the matrix product, so I will just do that for 2 of them and leave the others as an exercise. So let's consider, for example, the element C11 of the matrix product, which is obtained by considering the rows by columns product with the first row of A and the first column of B. You can see them represented here. If we perform the computation that we have learned, we have 1 times 3, there it is, plus 0 times 0, plus 1 times 1, plus minus 2 times 1/2. If you perform the computation, you obtain 3, which is the entry of position 1, 1 in the matrix product C. If instead you consider the entry C32, then you have to consider the third row of A, there it is, and the second column of B. There it is. Again, minus 1 times 1 plus 0 times 0 plus minus 1/2 minus 1 plus 3 times minus 3. Performing the computation, you obtain minus 19 divided by 2. In order to become familiar with the matrix product, it is important for you to perform all the other computations, and when you do so, you can check that the matrix product of A and B is the matrix written here. Now pay attention to the fact that the multiplication of two matrices is not in general commutative. This means that multiplying A times B is in general different than multiplying B times A. If you think about it for a second, you understand that this is something that has to be expected. In fact, matrix product represents the composition of linear maps, and it's not always true that if we compose F with G, we obtain the same result as composing G with F. You can check this with the example that I wrote here. Coherently with that, you can check that the matrix associated to this linear map with respect to the canonical basis of R2 and the matrix associated to this one again with respect to the canonical basis of R2, which are the matrix A and B respectively, don't commute in the sense that A times B is this matrix here, and B times A is this matrix here, and as you can see, these matrices are different. So remember, whenever F composed with G is different than G composed with F, we have that A times B is different than B times A. There are three particular cases of matrix product that it's worthwhile noticing. The first one corresponds to the case in which the matrix B is a column vector. In this case, the product A times B is again a column vector, but in general with different dimension with respect to the column vector B. The second case corresponds to the situation in which A this time is a row vector. The matrix A times B in this case is again a row vector, but in general with dimension different than A. Finally, we have the third case in which A is a row vector and B is a column vector, of course with the same dimension. The product matrix A times B in this case will be simply a scalar. For this reason, it is called the scalar product between the row vector and the column vector. In the course of Euclidean spaces, you will study in detail the concept of scalar product, and you will see the huge consequences that this operation has in mathematics and its applications. On a final note, I want to remark the fact that thanks to the matrix product, we can define the concept of product between two vectors, that is, their scalar product, which otherwise is not defined. This is another reason why it is interesting and useful to study matrices. Case 1, that is, when we have a product between a matrix with m rows and n columns and a column vector with n entries, deserves a special attention. In fact, we have seen that this matrix product gives rise to a column vector with m entries. Since the matrix product is a linear operation, this in turn defines a linear map that we call Fa between Fn and Fm, which takes the column vector v belonging to Fn and brings it to the column vector w belonging to Fm, obtained by multiplying A with B. As a nice exercise, I strongly invite you to check that the matrix associated to the map Fa with respect to the canonical basis of Fn and Fm is exactly the matrix A. This is something that we will use very often in the following. In fact, if we have a linear map F applied to a column vector V, instead of writing this, we will write the matrix product A times V, where A, of course, is the matrix associated to F. There is another important operation on matrices, which is called transposition and consists in swapping rows and columns. Formally, given this matrix here, its transpose matrix is denoted with this symbol, and it's the matrix which has rows and columns of A inverted. So if A is an M times N matrix, then its transpose is a N times M matrix. Explicitly, if you have this matrix here and you want to compute its transpose, you take the first row and you set it as the first column of its transpose. You continue, you take the last row and you set it as the last column of the transpose matrix. If this is not enough and you are in desperate need of a numerical example, take A to be 2, 1, 1.5, 0, 0, 1. Then the transpose matrix will have the first row of A as first column, so 2, 1, 1.5, and the second row of A as second column, so 0, 0, 1. Finally, let's list the properties of transposition. The first is that the transposition is an involution. In general, for involution, we mean an operation that repeated twice gives back the original object on which it is applied. In our case, if we apply 2 times the transposition, we come back to the original matrix, which of course makes sense, because the first transposition exchanges rows into columns, and the second transposition exchanges back columns into rows. The second property is that the transposition is a linear operation, in the sense that if we apply the transposition over the sum of two matrices, this is equal to sum the transposed matrices. And if we apply the transposition over lambda times A, this is equal to apply the transposed on A and then multiplied by lambda. Finally, whenever the matrix multiplication between A and B makes sense, we have that its transpose is the transpose of B times the transpose of A. So pay attention to the fact that the order is reversed. Consider a linear map F from the vector space V of dimension n to the vector space W of dimension m. Then recall that the image of F is the vector subspace of W given by the images of all the vectors of the domain vector space via F. In order to discuss the concept of image of a linear map from the point of view of matrices, we know that we have to fix two bases, one of V and the other of W, and then we can associate to F a matrix A with n rows and m columns. Plus, every vector V can be decomposed on the basis BV in order to give a column vector that belongs to Fn. Similarly, if we apply F to V, we obtain a vector that belongs to W, and so we can decompose it on the basis BW, obtaining a column vector that we denote again with W, and this column vector coincides with the matrix product AV. What I just said is visualized here, where on the left you have the functional picture, and on the right you have the matrix picture. Thanks to this consideration, and since the images of vectors belonging to the domain vector space by F are those that compose the image of F, we can define the image of the matrix A as follows. Given the matrix A with m rows and n columns, its image is the vector subspace of Fm given by all the vectors that can be written as the matrix product of the matrix A with a column vector V belonging to Fn. The dimension of the image of A is called the rank of A. We're now going to show that the image of A can be characterized in a more explicit and efficient way. To do that, we must explicitly perform this matrix product, obtaining this column vector here. However, as you can see, we can write this column vector as the sum of n column vectors like this. Notice that these vectors here have a particular form. In fact, the jth vector coincides with the jth column of the matrix A multiplied by the jth component of the vector V. Let's check what I said just for the first vector. We have that these entries here are exactly those of the first column of A, and then we have a constant that multiplies all these entries, and this constant is exactly the first component of the vector V. Since V1 is a coefficient, we can rewrite this column vector as V1 times the column vector given by A11, AM1. Why that? Well, we must interpret this as a matrix with m rows and 1 columns. And how do you define the product of a scalar times a matrix? Well, you multiply all the entries of the matrix by the scalar, which is exactly what it's written here. The fact that this is a column vector doesn't have to bother you, because a column vector is a particular instance of a matrix that has all the right to exist. So, to recap, we have that the product of the matrix A times the column vector V can be written like this, but we have already said that these are the columns of the matrix A that we denote with C1, Cn. And the final result that we obtain is that AV can be written as the linear combination of the columns of the matrix A with coefficients given by the components of the vector V. By definition, the image of A is given by all these images here, as V is allowed to vary in the vector space V. The consequence is that the image of A can be reconstructed by all the linear combinations of the columns of the matrix A. In the first chapter, we have proven that if we take all the possible linear combinations of a family of vectors, then we generate a vector space that is called the span of these vectors. Hence, what we have just proven is that the image of the matrix A is the span of its columns. But what about the rank of the matrix A? Well, the rank is defined as the dimension of this vector space, that is, the number of vectors that belong into any basis of the image of A. But how can we find a basis for the image of A, knowing that the image of A is the span of its columns? Well, that's very easy. Since the span of the columns generates the image of A, by definition, the columns form a system of generators for the image of A. So, in order to obtain a basis, we just have to select the linearly independent columns of A. So, to resume, the rank of A is the number of its linearly independent columns. Recall now that A is the matrix associated to the linear map F with respect to the basis BV and BW. So the question now is, can we use this handy characterization of the rank of A in order to characterize also the rank of F, in spite of the fact that we have performed a specific choice of the basis? The answer, luckily for us, is yes, and it's contained in this theorem. The theorem says that the rank of a linear map F between vector spaces V and VW coincides with the number of linearly independent columns of the matrix A associated to F with respect to any choice of basis of V and VW. So, in order to find the rank of a linear map, choose every basis you want of V and W, associate F to its matrix, compute the number of linearly independent columns of this matrix, and then you have the rank of F. If a matrix has n columns, then its rank is of course at best n. However, we can be more precise thanks to this very surprising theorem. For any matrix with m rows and n columns, the number of its linearly independent rows is exactly equal to the number of its linearly independent columns. Hence, the rank of the matrix is less than or equal to the minimum between m and n. This theorem is kind of shocking at first sight, right? Because if, for example, a matrix has a billion columns and just 3 rows, then the matrix has at best 3 linearly independent columns. An immediate consequence of the previous theorem is that the rank of a matrix coincides with the rank of its transpose. Let's now pass to the concept of kernel and nullity of a matrix. Given a matrix A with m rows and n columns, its kernel is defined as the set of vectors of Fn such that this matrix product gives rise to the null vector of Fm. It can be proven that the kernel of A is actually a vector subspace of Fn, and its dimension is called the nullity of the matrix A. After the discussion that we had before regarding the image of a matrix and its rank, this theorem shouldn't come as a surprise. Given a matrix A with m rows and n columns, the kernel of A is isomorphic to the kernel of F, where F is any linear map associated to A independently of the choice of the basis of Fn and Fm. Being isomorphic, these two vector spaces have the same dimension, and so the nullity of A is equal to the nullity of F. Thanks to this result, and also the previous one regarding the rank of a matrix, we can extend to matrices the nullity plus rank theorem. Recall that if we have a linear map between two vector spaces V and W of dimension n and m respectively, then the nullity plus rank theorem says that n, the dimension of V, is equal to the nullity of F plus its rank. So, whenever we have a matrix A with m rows and n columns, we have that n is equal to the nullity of A plus its rank. This theorem has two noticeable consequences that are written here, and in order to understand them, we must come back for a second to page 42. At page 42, we have proven these two theorems here, which said that the linear map F between vector spaces V and W is onto if and only if its rank is equal to the dimension of W, and we also say that the map is full rank, and F is one-to-one if and only if its nullity is 0. We have also seen that for an endomorphism, the fact that the nullity of F is 0 implies that the map is full rank and vice versa. And so it is enough to show that either the nullity of F is 0 or the rank of F is full in order to show that an endomorphism is an isomorphism. We have recalled what we need in order to understand the consequences of the nullity plus rank theorem for matrices, and we can get back to page 66. So we are now at page 66, and let's recap what we were saying. We have a linear map F from vector space V to vector space W with dimensions n and m respectively. If we fix any basis of V and of W, we can associate F to the matrix A that will have m rows and n columns. In this context, the nullity plus rank theorem says that n equals the nullity of A plus the rank of A. And we also know that the nullity of A is exactly equal to the nullity of F, and the rank of A is exactly equal to the rank of F. Let's consider the case in which n is less than or equal to m, and suppose that the rank of A is n. Since here we have n and here we have n, this implies that the nullity of A is 0, and so also the nullity of F will be 0. This means that A represents a one-to-one linear map. Notice that we can only say with certainty that A represents a one-to-one linear map F. In fact, M could be strictly larger than N, and in this case, F wouldn't be full rank. However, in the case in which the rank of A is N, and N coincides with M, which is satisfied, for example, by endomorphism, then A is not only characterized by having the nullity equal to 0, but is also full rank. And so every linear map associated with A will be an isomorphism. As I wrote here, in the case of a matrix with the same number of rows and columns, we say that the matrix is square because the table of its scalar entries has the shape of a square. In the next page, we are going to examine an example to better understand these results. Consider this matrix, which has 4 rows and 3 columns, and so it represents a linear map between R3 and R4 with respect to any basis of these spaces that we may choose. The nullity plus rank theorem applied to this case says that 3 is equal to the nullity of A plus its rank. Since the number of columns of A is 3, we have that the rank of A is at best 3. Let's check if the columns of A are linearly independent or not in order to see if the rank of A is indeed 3 or less. If we perform a generic linear combination of the 3 column vectors with these coefficients here, we obtain this vector here. If we impose that this vector is equal to the null vector of R4, we obtain a vector equation that we know is equivalent to this system, and if we solve this system, we obtain that all the coefficients of the linear combination are null, which means that we can recreate the null vector of R4 with the 3 column vectors just using null coefficients. That is, the 3 column vectors of A are linearly independent. So the rank of A is 3, and this implies that the nullity of A is 0. Hence, every linear map F between R3 and R4 that is associated to A with the choice of any basis will be a one-to-one map, but not an onto map.
In this short video, I want to stress again the importance of the concept of rank of a matrix. Consider the matrix A with m rows and n columns, then the image of A is defined as the span of the columns C1, Cn. The rank of A is defined as the number of linearly independent columns of this matrix, and so it determines the minimum number of columns that can be used in order to reconstruct the image of the matrix. Quite unexpectedly, the number of linearly independent columns of A is equal to the number of its linearly independent rows, and so the rank of A is less than or equal to the minimum between M and N. Keep in mind the concept of rank because it will have a huge importance in Chapter 3 when we will deal with systems of linear equations.